Good afternoon. It's my pleasure to welcome you again to this, our second session for this morning of the Science Symposium 2019, sponsored by Urantia Foundation, and we're again here at 533 Diversity. At this time, Phil Calabrese is going to give a presentation. Phil, as many of you know, he probably really doesn't need an introduction. He's done many presentations on scientific issues in the past. Phil has a BS, an MS, a PhD in mathematics from Illinois Institute of Technology, where he published an original paper on infinite series as a sophomore, and was later awarded a 3-year NASA traineeship for graduate school. During a subsequent 15-year teaching career at several universities and colleges, and 10 years as an aerospace analyst and scientific programmer, he invented an algebra of Boolean fractures, better represented and combined certain conditional information. For this work, published in 1987, he was awarded a 3-year National Research Council Associateship that supported further development of his algebraic synthesis of logic and conditional probability. In 1993, his personal company, Data Synthesis, won a 3-year prime contract from the U.S. Navy to develop techniques for uncertain conditional information processing, TUCIP. More recently, he has applied his algebra to obtain more natural expression of quantum logic. In 2017, Phil published Logic and Conditional Probability, a synthesis in the Studies in Logic series of college publications. He continues to review papers on the formations of quantum logic for the American Mathematical Society's Mathematical Reviews. Phil's early education came at the hands of Roman Catholic nuns, followed by Dominican priests at an all-boys school, high school, where he learned the philosophy of Thomas Aquinas. After having a religious experience in late 1969, the Urantia book found him in August of 1970. At California State College, Bakersfield, he initiated and taught the first for-credit college course on the Urantia book. Since then, he has authored numerous papers and presentations dedicated to the Urantia book, especially on its unique cosmology. Phil is a father of 4 children. I present you Phil Calabrese.
Thank you, Ralph, for that very generous introduction, which I wrote. When Joanne said, "I put you after Nigel," she had a little smiley face after it. Now we know why. So I'd like to thank everyone for the opportunity to present some of the new cosmology offered by the Urantia book. And thanks to the trustees and employees of Urantia Foundation, to Ralph Zaire and Joni Strobel and Jennifer Siegel and my fellow presenters for supporting the scientific credibility of the Urantia book. My paper has 2 parts. I'm only going to be really presenting the second part, except for this brief introduction. The cosmology of the Urantia book differs from the presently accepted cosmology of Earth's cosmologists in some very crucial ways. Perhaps the most striking difference is that in the UB cosmology, cosmology has an absolutely fixed gravitational center, which, while not in space, can nevertheless be located at the focus of space. By contrast, Albert Einstein propounded a special relativity theory with no absolutely fixed reference frame. In Einstein's cosmology, any reference frame may be considered fixed, and motions measured with respect to it. Another big difference in the cosmology of the Urantia book versus contemporary science is the geometric concepts associated with the particles described in the Urantia book. Particles all have a relatively fixed central nucleus around which spin peripheral space energies at speeds beyond imagination. By contrast, formal contemporary cosmology has abandoned geometric descriptions of ultimate particles, quanta, preferring to endow, quote, point particles, unquote, with infinite space extension to account for wave interference properties, plus velocity, momentum, and spin to account for quantum properties. The Urantia book affirms the existence of open space energies that produce energy waves that affect moving particles. Contemporary science is just now beginning to imagine such pre-mass energies through which particles swim. In part 1, Gravity and the Center of Inertia, I recount a little-known solution of Einstein's field equations of relativity by the famous logician Kurt Gödel. That includes a fixed center, rather than an absolute relativity as arbitrarily postulated by Einstein. In part 2, Quantum Entanglement, Spooky Action at a Distance, Bell's Theorem, and the pre-quantum energies of open space, I explain, using the Urantia book's cosmology, the mysterious spooky action at a distance phenomena called quantum entanglement. So let's move on to that. You can read the first part in the paper that will be made available. So let's move this to the next slide. Here's good old Albert. He called quantum entanglement spooky action at a distance, and he tried hard to prove it didn't exist. This phenomenon was already evident in the double slit experiment performed by Thomas Young in 1801 and extended to particles in 1927 by Davison and Germer, when light was later shown to be a particle, a quantum, not a wave. By Einstein, the mystery deepened. Now, in this picture, and I borrowed this from, I guess, maybe Wikipedia. This electron gun could be a photon, or it could be an electron or some other particle. This is a famous double slit experiment. And the light, you know, you shoot these particles, and they got it down to one at a time. And if there are two slits, well, if there's one slit, what you expect is to get a bulge behind it on the photographic plate. No problem. But if you have two slits close together and you shoot particles like photons, it turns out the light is always found to be absorbed at the screen at discrete points as individual particles, not waves. The interference pattern appearing via the varying density of these particle hits on the screen. Einstein had explained the mysteries of radiation from a heated black body, but he made the double slit experiments even more mysterious. how could particles of light, each going through one or the other slit, know where to hit the photographic plate behind the slits to make an interference pattern in their aggregate? All right, well, let's move on to the most important entanglement experiment. Recall that a particle can independently and simultaneously spin on three perpendicular axes: roll, pitch, and yaw. For instance, of a rocket. There are rotations on three perpendicular axes, and they're depicted here, I thought, fairly well. Opposite rotations on the same axis have opposite signs, or plus or minus. So you can see in this that, a rocket could pitch, it could yaw, and it could also, roll. I may have got those mixed up, but you get the point. Three different possible spin types. Well, famous experiment, Stern-Gerlach experiments exhibiting particle entanglement. Imagine that there is a central area where a particle splitting zone. You can see that there. I guess I can use this, but you can't see that. You can see where I got those two little zeros there, and you start with a particle that's not spinning in any of the axes, and they split it, and I won't try to go into the techniques of that, but these particles split and move into opposite directions, and you set up two sensors that are large enough distance to preclude any influence at the speed of light. And then you have two sensors, usually called Alice and Bob, but anyway, sensor 1 and sensor 2. And at these two sensor locations, you measure the spin on the split particle, one side or the other. And, well, what spin do they measure? Those are randomly chosen on each side and independently. So so there would be three different axes on the left side and three different axes on the right side that could be measured. And so you can see on the left side here, let's say data from S1 is on axis A, you got a plus. And on the other side, you measured A and you got the opposite spin. The next time they make a simultaneous measurement, S1 gets B, axis measures B, and it gets a negative. On the other side, maybe axis C was measured and it got a positive. So they do that hundreds of times, maybe thousands of times, and then they pair the data in the middle. They join and say, okay, well, left A plus minus A minus, left B minus plus right C plus. And you can see three dots there that indicate a whole lot more measurements. So the vertical dots at the bottom represent hundreds of simultaneous paired measurements, enough to make two experimental observations. What they find is that whenever Alice and Bob happen to measure spin on the same axis, A, B, or C, their measured values, plus or minus, always disagree. And apparently this is because the original composite particle started out with 0 spin, so that if Alice's particle spins one way, Bob's is going to spin the other way to preserve angular momentum. In other words, for the subset of data points or pairs with both sensors measuring the same axis, the probability that they disagree in sign is 1. They always disagree when they happen to measure the same axis. So this is a conditional probability. It's the probability that S1 is plus and S2 is minus, or that S1 is minus and S2 is plus, given that they measure the same axis. So remember that. So I've restated it here. Nevertheless, over the whole population of hundreds of paired measurements, Alice and Bob still disagree, I say, only about half of the time, half of all these joined data. That is that overall, the probability of S1 and S2 measured spin values disagree is still only 1/2. Well, there's a problem in that. So by observation 1, it is deduced that whenever they leave each other, the two splitting particles have opposite spin values for each of the 3 spin axes, A, B, or C. For example, if the left particle has spin plus, minus, plus for the axes A, B, and C, respectively, then the right particle has the opposite spin values, minus, plus, minus, for those 3 axes. That seems like a reasonable deduction, considering that whenever they measured the opposite, they measured the same axis, they get opposite values. So now we're thinking, well, when they left, the particles must have had those properties. Well, Bell's theorem, John Bell, he says, assuming the particles have enduring local spin values, in other words, they carry those spin values as they leave and keep them for each of the 3 axes, the above statements are statistically impossible unless the spin values of each particle are somehow influenced by, in other words, depend upon, the distant spin measurement of the other particle. So something's happening there, it would appear, faster than the speed of light. Now this is the hardest slide you'll see, and I see that it did not quite come out the way it should have, and that's too bad. Unless I don't think I can change this, but the second line is shifted over, I guess, to the left. You got to imagine that is moved over. And it's too bad that this is the way it is. I wonder if I can...
No, we get it.
We can see.
Yeah. Well, it's going to be harder. I don't think I can change anything here, can I?
No.
All right.
Don't worry about it.
All right. I'll say things here, and you can probably get what I'm saying. Notice that based on the particle spin implication that was just stated, for example, if the left particle spin has plus, plus, minus, as in second row, put all possible left particle spin types over here on the left. It's either plus, 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 minus, plus, minus, plus. You know, there are 8 possibilities for 3 axes, either plus or minus. And on the other side, there would be the opposite values for the right particle. And now at the top, I have all the possible combinations of measuring axis on the left versus the right. It could be that they both measure A as in the top, or the left measures A and the right measures B, or the left measures A and the right measures C. Or it could be that the left measured axis B and the right measured axis A, or the left measured axis B and the right measured axis B, and similarly all the way through to CC. So there are 9 possibilities for measuring axes: AA, AB, AC, BA, BB, BC, CA, CC, CB, or CC. And on the right, we don't even know exactly what those probabilities are that we get those particular rows. So they're going to be row probabilities: x1, x2, x3, x4, x5, x6, x7, and x8. Unknown, but they're all just probabilities, and they have to add up to 1. So you can see the 1 at the bottom there on the right. Each of the 9 possible measurement pairs have 1/9 probability because they're doing this randomly on both sides. So that's why there's 1/9 at the bottom. The first column has a 1/9 probability, and etc. down to the ninth pair, CC. So now consider when these measurement pairs would differ. Well, if you're in the top row, where the left particle is plus, 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 and the other particle is minus, 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 they're obviously going to disagree. Because no matter what which axes they measure, the left's got pluses and the right's got minuses, so you'll see that at the top I've got 9 D's. 1, 2, 3, 4, 5, 6, 7, and 8 are too close, and 8 and 9 are okay. Anyway, all of those are D's. And the same thing is true at the bottom. If the left particle is minus, 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 then the right particle is going to be plus, plus, plus. Therefore, the measurement's going to have to disagree. So that's why I've got D's all the way on the bottom. Now, the middle 6 rows, you'll notice, let me take one that's not screwed up. And I think I used the second one in my paper, but well, let's take the third one, let's take this one here.
Yeah, spin value.
Yeah.
Spin value, this one.
Yeah, that one's good.
So you gotta say, well, when would they disagree and agree? Well, if the left sensor measures A, well, wait a minute, before I get to that, you'll notice that the hypothesis, if they both measure the same axis, AA or BB or CC, they're going to get a difference because they're measuring the same axis. That's what we discovered by experiment. So there's D's all along AA or BB or CC. So when you look in the middle rows, when do they agree? When would they ever agree? Well, say this one here, if I have a plus, minus, minus, well, they'll agree if one measures A and the other measures C. Or if one measures B, if the left measures B and the right measures C. Because if it's minus, minus, it'll be plus, plus over there, and then you'll get a different spin. So if you look at that, you realize that there are 4 cases which are measured there, A, and then there's one more A in that row. And it's basically, if this is the particle, you've got to have one measuring B and the other measuring C. So AC or CA, or it could be the let's see if I got that right. We want to see when are they going to agree. In order to agree, you got to have A and B or A and C measured, because remember the particle spin is opposite on the other side. So if they're going to agree, you got to measure plus A here and B, which will be get you a plus on the other side, or A and C. And then of course it could be that the left sensor measures one of them and the right measures the other. So you get 4 chances for agreement in each of those rows, and 5 chances for disagreement. Okay, I hope you got that. It's not too simple, a little subtle. So again, each of the 9 columns has equal probability, 1/9, of occurring, because the 2 sensors randomly and independently choose one of the 3 axes, A, B, or C, on which to measure spin. The ith row has unknown probability, xi, but the sum of these 8 xi's must be 1, because the particle spin triple must be one of those 8 possibilities. The probability of a particular measurement axis pair, which would be the column J, and a particular particle spin value, triple, which would be the row, would be 1/9 times whatever the probability of that row. Because the row in which the particle belongs depends on the splitting process and is independent of the axes randomly chosen by the 2 sensors. The probability of both of 2 independent events occurring is the product of their individual probabilities. So note that the sensors never agree on rows 1 or 8. If the left particle has positive spin on all 3 spin axes, I'm repeating myself, but probably that's not too bad, then by the implication, the right particle has negative spin on all 3 axes. So note also that each of the other 6 rows contribute exactly 4 agreements and 5 disagreements. So using this table, we can now express the probability of A that the sensors agree. The probability of the sensors measuring the same sign, that is, agree, is, well, if it's in the first column, well, we never get any disagreement there, so it's 0/9. In each of the other ones, 2, 3, 4, 5, 6, or 7 rows, we each time get 4/9. And on the final row, I guess it's the row, first row gives 0, last row gives 0, and each of the other middle rows gives 4/9. So 4/9 is a common factor there. I factor that out. You get, and the zeros go away. So you get x2 plus x3 x4 plus x5 plus x2, 3, 4, 5, 6, and 7. Well, they have to add up to 1 totally. So if I stick in 1, then I'm making a larger value. So I get 4/9 times 1, which is equal to 4/9, which is less than a half. But wait a minute. This contradicts the experimental observation that I said. Overall, they still agree 50% of the time. They did hundreds of these. They look at them and they say, well, somehow agree catches up with disagree somehow. How is that possible? The particles are somehow entangled. Measurement of one affects the measurement of the other at faster than light speed. That is the essence of the issue. What's a possible explanation? There's mutual sensor influence at faster than the light speeds. Measurement of one particle somehow affects the property values of the other particle. The measurements are not really independent. You know, you measure here, you think it's independent of the one over there, but something's happening that makes them not totally independent. Another possibility is that the particles are really also extended waves that can interfere with each other, but instantly become localized when measured. This is called instantaneous wave-particle collapse. Particles don't really carry local reality spin. They somehow or other, they lose local reality in that hypothesis. And that's more believed now by contemporary physicists than the other. So this Copenhagen interpretation, it was in 1926, he proposed the wave theory of quantum mechanics, believing he had, Schrödinger did. He thought he had found real waves, a new phenomenon, quantum waves. And de Broglie had suggested this 3 years earlier. The competing Copenhagen interpretation identified the particles and waves and informally called them wavicles. Supposedly, material particles were also waves. Soon, scientists altogether discarded visualization efforts and merely assigned properties of position, velocity, mass, spin, and so forth to point particles. Point particles, without any concept of their internal geometric properties. Quantum mathematics predicts the observed probabilities, and that is pretty much where things now stand. Well, in the 1950s, physicist David Bohm showed, and Nigel mentioned that the quantum entanglement could be explained with particles having local properties of spin, such as spin, as long as faster than light interference was caused by what he called guiding waves. Although this interpretation is not presently the standard, it produces the same experimental data, and it is consistent with what the Urantia book says. Well, now I've got some quotes from the Urantia book that are relevant. Ultimatonic rays. The assembly of energy into the minute spheres of ultimatons occasions vibrations in the content of space which are discernible and measurable. So this suggests that there is something like a phase change going on as pre-particle energy condenses into particles like dewdrops form in the air when the air temperature falls. I had a chemistry professor who said, well, you're going to think about this in a long time from now. This is first year chemistry. He said, but I think there's a phase change going on. They don't think so, but I think so. And I keep remembering that guy. Here's another one. The undifferentiated force blanket. The so-called ether is merely a collective name to designate a group of force and energy activities occurring in space. Ultimatons, electrons, and other mass aggregations of energy are uniform particles of matter. And in their transit through space, they really proceed in direct lines. Light and all other forms of recognizable energy manifestations consist of a succession of definite energy particles which proceed in direct lines except as modified by gravity and other intervening forces. That these processions of energy particles appear as wave phenomena when subjected to certain observations is due to the resistance of the undifferentiated force blanket of all space, the hypothetical ether, and to the intergravity tension of the associated aggregations of matter. Intergravity tension. The spacing of the particle intervals of matter together with the initial velocity of the energy beams establishes the undulatory appearance of many forms of energy. The excitation of the content of space produces a wave-like reaction to the passage of rapidly moving particles of matter, just as the passage of a ship through water initiates waves of varying amplitude and interval. Primordial force behavior does give rise to phenomena which are in many ways analogous to your postulated ether. Space is not empty. The spheres of all space whirl and plunge on through a vast ocean of outspread force energy. Neither is the space content of an atom empty. Nevertheless, there is no ether, and the very absence of this hypothetical ether enables the inhabited planet to escape falling into the sun and the encircling electron to resist falling into the nucleus. So, thus, the Urantia book affirms that the waves are separate from the particles and that they consist of compression waves within the energy content of space. Since these waves are in pre-mass energy medium, they are not subject to Einstein's constraints of light speed as the maximum speed of all moving particles. Here I'm going a little further and saying, well, it's more of what the Urantia book says. The Urantia book confirms Einstein's E equal mc squared equation. The quantity of energy taken in or given out when electronic or other positions are shifted is always a quantum or some multiple thereof. But the vibratory or wave-like behavior of such units of energy is wholly determined by the dimensions of the material structures concerned. Such wave-like energy ripples are 860 times the diameters of the ultimatons, electrons, atoms, or other units thus performing. That is, the ratio of the wavelengths associated with these particles to their diameters is 860. Which must be a property of the force energy content of space. I'm saying, since the energy of a wave is inversely proportional to its wavelength, the particles of smallest diameter are associated with the waves of highest energy. In the superuniverse of Urantia, there are 100 octaves of wave energy, according to the Urantia book. Each octave represents a doubling or halving of the wavelengths of the preceding octave. Therefore, there are likely particles ranging in diameter, d, from that of the ultimaton through particles of diameter 2d, 4d, 8d, 16d, etc., up to 2 to the 100d, to give rise to 100 octaves of wave energy. 2 to the 100 is a whole number with 31 digits. So the largest particles are 10 million trillion times the size of the ultimaton, according to that hypothesis. And the ultimaton has a diameter of 1/860th of the waves of shortest wavelength. Very small. Well, that concludes my prepared notes. And I guess I'm ready for questions.